Welcome to a brief overview of our work, Sparse PointPillars, maintaining and exploiting input sparsity to improve runtime on embedded systems. To speed up neural network object detectors, practitioners typically use model quantization and weight sparsification. In this work, we take a third orthogonal approach by developing an architecture that exploits input sparsity to reduce computation built around point pillars, a very popular, fast, high-performance bird's eye view 3D object detector. Point pillars operates by taking in a point cloud, pillarizing the scene into a regular grid, and vectorizing the non-empty pillars, producing a pseudo-image. Importantly, these point clouds are highly sparse, so almost all pillars contain no points. Point pillars leverages this sparsity by gathering the non-empty pillars in a sparse coordinate matrix, a matrix that stores the position and value of non-zero entries, and vectorizes the non-zero pillars. But it then scatters these feature vectors back into a dense matrix representation of the pseudo-image using coordinate lookups. The backbone, a feature pyramid network, performs dense convolutions, resulting in shrinking and string of the pseudo-image. As you can see in this example from the KITTI dataset, the input pseudo-image is highly sparse, but point pillar's backbone makes no attempt at maintaining or exploiting this property, leading to many unnecessary convolutions. This begs the question, what if we use this natural sparsity to speed up the backbone? This is where our work, Sparse PointPillars, comes in. We maintain the natural COO sparse matrix format coming out of the feature net, passing it directly to the backbone, which leverages the COO representation to maintain and exploit its sparsity throughout the feature pyramid via sparse and submanifold convolutions. Our backbone doesn't just use sparse convolutions because they are mathematically equivalent to dense convolutions, causing the same smearing of non-zero entries as seen in the point pillar's backbone. We want to prevent this smearing to maintain sparsity, so Sparse PointPillars backbone uses submanifold convolutions, or sub-MCOMs, which only run centered on non-zero entries, avoiding smearing and thus both maintaining and exploiting sparsity. We theoretically analyze Sparse PointPillars' modified backbone, providing theoretical upper bounds on the number of convolutions performed by Sparse PointPillars, and we experimentally validate our backbone's changes on two datasets. First, we run on KITTI, the self-driving car 3D object detection dataset used in the original point pillars paper, where we compare our changes against standard point pillars, along with several ablative models featuring hybrid, sparse-dense backbones and a backbone with wider convolutions. We report runtime results on a high-end desktop, as is typical in the vision literature. Sparse point pillars has a very minor runtime improvement over point pillars, with a 5 to 9% decrease in AP, with the ablative models performing similarly poorly. However, the KITTI dataset is from a self-driving car and not representative of the types of tasks required for mobile service robots or other embedded systems. To simulate a realistic service robot task, we constructed Matterport Chair, a novel chair detection dataset sampled from the perspective of a service robot in homes from Matterport 3D, a dataset of real home meshes containing object-bounding boxes. We evaluate point pillars in our method's runtime on a high-end desktop, as well as a JetSet Xavier, an embedded ML accelerator with multiple power settings, and the CPU of a fetch freight robot, a high-end robot base without an ML accelerator. Sparse PointPillars runs faster than point pillars by a factor of 1.5x on desktop, 1.8x on Xavier's high power setting, almost 3x on Xavier's low power setting, and more than 4x on robot's CPU, all at the cost of about 4 to 6% AP. As an example of the value provided to practitioners, Sparse PointPillars on Xavier's 10-watt, 2-core power setting is actually faster than point pillars on Xavier's 30-watt, 8-core power setting, allowing practitioners to reduce latency and power consumption by switching from point pillars to Sparse PointPillars. Altogether, these results demonstrate that Sparse PointPillars provides a new tool in the practitioner's toolbox for tuning their perception pipeline. A link to our paper, along with the full release of all code, dataset, and model weights are available at our project page, better.io/SparsePointPillars.